I will, as I said, there is this theorem of Wang that הפעלתם את ה... אז... So Wang theorem says that it's finite, but Wang theorem, one proof was completely ineffective. Basically, it's a beautiful proof. Sometimes the most beautiful proofs are how do you show that something is finite? So the most beautiful proofs cannot be effective. Like, for instance, there is this theorem that we discussed in the Midrasha, this normal subgroup theorem. So it shows that sometimes you have a group such that every subgroup of every normal subgroup is a finite index because the quotient must have two properties that contradict each other, like amenability and property T, which makes it a finite quotient. So here, also there is a nice idea. In a sense, Wang considers a space that parameterizes all lattices in G, in this Lie group, and it shows that if you bound the volume from above, you get a compact space. It becomes a compact space, and the conjugacy classes are open there, so it will be an open cover of a compact space. It must be a finite. So in a sense, if you introduce a topology, we will do that, but you introduce a topology on the space of conjugacy classes, lattices, such that if you bound the volume, you get something which is both compact and discrete. So it must be finite. But it gives no estimate at all. So to get an estimate, you need a different approach, and we will do that. Okay, we will do that at some point. Now, there is another natural question. You can, instead of counting up to isometries, split up a body. This is up to isometries. You can be more rough. You can be rougher and count up to commensurability. So definition. Two manifolds, M1 and M2, are called commensurable if there is a manifold, if there is a common finite cover. I mean, there is a manifold M3 that cover both. Maybe this is covers of maybe this is an n-sheeted cover and this is an m-sheeted cover, but there is a manifold so that covers both. Then I say that then M1 is equivalent or commensurable to M2. And and let's say that I want to count manifold up to commensurability. So you can ask a question, okay, you define, let's say, Cn of V to be number of n hyperbolic complete manifold up to commensurability. And here there is a nice what?
A volume estimate.
A volume estimate. And here there is a theorem by Ariel Levitt and myself, which we showed. Okay, here, I'm skipping some theorems, but this is a theorem from a few years ago. With Ariel Levitt, we show that for, let's say, n at least 4, Cn of V behave Cn of v, if you look at let's say log of Cn of v, is bounded by b v log v from above and a v log v from below for sufficiently large v. This is needed for the lower bound. The upper bound is too.
And A and B depend on N?
For some A and B, there exists A and B, depending on B, depending on N, and such that this one. So in particular, so the number Cn of v, if you look at it, it's in a sense like v to the v. It behaves like v to the v. And why I like this theorem? One reason is that if you consider, I didn't define, but suppose we restrict ourselves to arithmetic manifold. So see, the number of parabolic for manifold is super exponential. But if I restrict to arithmetic one, you will get only polynomially many. So these theorems tell you something
Qualitative?
There is some qualitative corollary that most hyperbolic manifolds are non-arithmetic. We will see, or maybe you know, we will mention arithmetic theorem that in some Lie groups, in higher rank, for instance, in SL3 are all lattices are arithmetic. This is the fundamental theorem for Gulick's. And in rank 1 group, like SON1, it's not true. There are non-arithmetic examples, but the construction of them are non-trivial. So it took some years until people knew to construct a non-arithmetic manifold of every dimension. This is the classical theorem of Gromov and Piazetti-Shapiro, which we will discuss. They show how to construct a non-arithmetic manifold in every dimension. They construct a single one. I mean, by the same construction you can construct many, but you can construct several, but they construct one in every dimension. This theorem tells us that actually most manifold, if you take a random manifold, it will be non-arithmetic.
So this was a known before theorem?
What?
Like that they were most.
No, what was known is that Gromov and Piazetti-Shapiro proved there is a beautiful paper in Journal of IGS of Gromov and Piazetti-Shapiro that construct. Actually, I think they constructed them in explicitly only in even dimension and deduced that there must be also in odd dimension. They didn't even. You can do what they did in any dimension, but you just get one manifold. You don't have a control on its volume, so and yeah.
So how does CNV grow for arithmetic?
So for arithmetic, it's polynomial. I was vague about it. I conjecturally, it goes polynomially. There is a polynomial that's bounded for arithmetic. And this conjecture you can prove for non-uniform one. For uniform, you know that it's almost polynomial. You know that you know what can you show for you know that v to the it's bounded by v to some constant, but you have what do you have here? A constant log v to the epsilon, something like that. It's bounded by this. For arithmetic, but epsilon you can take arbitrarily small. When you take smaller epsilon, you pay by larger alpha. So this you can show for this you can show, and conjecturally you don't need this. Anyhow, this is much smaller than and okay, so this is about counting. I will discuss this in details and in enough details so that you can actually compute this constant if you want. And some people care about this constant. I never cared about them because it's technical, and if you really want to explicit constant, you have to do tedious computation. But several people asked me over the years about constant because there are applications for the constant. I was never bothered about it, but if someone wants, there will be many constants in this course that one can compute, and sometimes there are reasons to do that. But, okay, this is about counting. We will discuss counting, but there are many. So maybe I will also mention. So the first paper about counting was a paper of myself with Lubotsky, with Mark Burger and Shachar Moses, when we count up to isometries, and we got the same estimate like with Aryeh, but not up to conjurability, but up to isometries. And the upper bound, of course, if you count up to isometries, there are more than up to conjurability, but the lower bound was somehow easier to do. And the lower bound, we did, all what we got was commensurable manifold. We used the subgroup growth theory, a nice proof of Alex, but one thing that the reasons to do that was actually it came from physics. So the people who asked this was astrophysicists, and they needed this estimate for some computation related to the cosmological constant, and they used our estimate on the number of n-dimensional or four-dimensional manifolds. I don't know to explain more than that, but I can refer you to the papers. And yeah, somehow, if you believe relativity theory, so there is a Lorentz transformation, and we live in a Lorentzian space-time, so it's like the hyperbolic, metric. It's also determined by Lorentz form. So I don't know. So it's related to the outside world, maybe. This is about counting, but you can ask much more about. You can ask much more about. Basically, I remind you the basic question is what can we say? What the volume tells you about the complexity of the topology. So, can you bound the complexity by the volumes? That was, in a sense, the original question. For instance, the homology of M is a abelian group. Is a abelian group. And you can show that the homology of M is Z to the Betty number plus some group which called tau, which all the elements are a finite. It's a torsion group. It's a abelian group such that every element is finite order. And Gromov showed that this Betty number is bounded by the volume. That's the first theorem I mentioned. And he also showed that this group is finite. So Gromov showed that hk of m is, it shows that the Betty number are bounded by the volume up to a constant, and he also showed that the torsion group is finite. I think both he did it in 78, but he didn't give an estimate for this. And in fact, he showed that you cannot give an estimate by producing a sequence of manifold of dimension 3 such that the first torsion, for k equals 1, goes to infinity and the volume is bounded. And he did it before Thurston constructed the example I drew before the break. So in Gromov's construction, it was not a constant curvature, it was not hyperbolic, but it was negatively curved, which was enough to demonstrate his theorem, because his theorem was, this theorem of him is about, you don't need constant curvature, so he showed that the torsion cannot be bounded. And if you use this Thurston construction that I mentioned before the break, you can actually do it for hyperbolic manifold. You can have a sequence of hyperbolic manifold of volume, 3 manifold of volume less than 2.03, such that the torsion goes to infinity. The torsion is always finite, but it goes to infinity and the volume is bounded. So in a sense, you cannot bound the torsion. But it's only a 3-dimensional phenomena. So this is another theorem that with Uri Bader and Roman Sauer we proved recently. So I like to call it BGS2 because, as I said, this theorem of Gromov I call BGS1 because it's in the proof is in a book by Bauman, Gromov, Schroeder. So this is like BGS2. So it shows that for n which is not 3, we have that in dimension not 3, the torsion is bounded. Log of the torsion is also bounded by c times volume. And log, as we will see later, this is the natural things we want, to bound the log of the torsion. So this is 2 in dimension not 3. So as it also demonstrates the fact that 3 dimension is the most interesting. But you can control things in either dimension, and the torsion in homology became very interesting in mathematics in recent years because of application to number theory. So many people are interested in torsion in homology. So this was one of the motivations for us to prove this theorem. But this is another type that demonstrates the fact that the volume does determine the topological complexity.
Does C depend on K2 or only on?
C depend. You can take C that depend only on n, of course, and the only finitely many k, right? So take the maximum. But k is up to the dimension. But yeah. Okay. So now, but now I want to say some conjecture which is stronger than bounding the topological complexity, and this conjecture will accompany us for a while, because we would like to prove this conjecture, and we still don't know to prove it in general, but so how do we try to estimate the complexity? How can you pronounce the complexity of a manifold? So one idea is to simulate the manifold by combinatorial object, like triangulate the manifold and count how many triangles you mean or how many simplices you need. Something a bit more general is to find a simplicial complex that is homotopy to the manifold. And so this is a definition. Let's say dV simplicial complex in short I will write dV simplicial complex. I will write like this. Is a simplicial complex with at most V vertices and all degrees all are bounded by D. So a simplicial complex, it has vertices, it has edges. The one skeleton is a graph. And in this graph, the degree, I want to have at most V vertices, and the degree of each vertex, I want to be bounded by D. So this is somehow to say how complicated is the simplicial complex. And one remark, you can ask me, why do you care only about the first skeleton? Why don't you bound the number of 2 simplices, or 3 simplices, or n simplices? And the reason is that if I bound the number of vertices and the degrees, I can bound all the rest. So for instance, so remark, the number of, let's say, 2 simplices of such a dV simplicial complex is bounded by, let's say, V times D over 2, right?
Containing a given
V times, sorry, the number of edges is bounded by this. The number of 2 simplices is V times D choose 2 divided by 3.
When you fix the vertex and look at all the 2 simplices containing it, or
Yeah, I fix a vertex, so I have V choices for the vertex. In each of them, there are at most D edges. And from these 2 D vertices, from these D edges, there are only D choose 2 way to choose 2, and these 3 maybe define a simplest and maybe not. So this is this D choose 2, V times D choose 2, but then the simplest I count 3 times, so I divide by 3. Okay? So, and similarly, the number of K simplices is bounded by V times D choose K divided by K factorial. Right? Or K plus 1. K plus 1. D choose K divided by K plus 1. Okay. So, so if you bound the number of vertices and you bound the degree, in a sense you get a bound on the side of the simplicial complex. In particular, the dimension is bounded by D plus 1 by D, okay, and later D will be a constant and V will be the volume. So you see that all this formula that we get, V appear 1, so it's linear, depending linearly on V. So it's good for what we're aiming for. And now the conjecture. So the conjecture, again, it's not the most general formula, a formulation of the conjecture, but it's quite general. So conjecture given n, there constants d and alpha such that any complete hyperbolic n manifold is homotopy equivalent to a d alpha volume M simplicial complex. So this is a conjecture I would like to prove because it will have plenty of application. And this conjecture as written is false. So let's, instead of saying n is not 2, let's say that n is not 3. It's 2 in dimension 2. In dimension 2, Gauss-Bonnet tell us everything about the manifold, topologically. In dimension 3, because of Thurston construction, we know that basically, let me say why it cannot be 2 in dimension 3. Because it says that if I bound the volume, then I bound the complexity of the homotopy type. The homotopy type is the same as the simplicial complex which is boundedly many vertices and bounded degree, so there are only finitely many such simplicial complexes. For a given V and D, there are only finitely many dV simplicial complexes. And I can actually estimate how many. I can count them. So if I bound the volume, it must bound the manifold if I count them up to homotopy. Now, most rigidity tell us that in dimension 3 or more, counting up to homotopy is the same as counting up to isometry. But Thurston tell us that in dimension 3, if you bound the volume, there are still countably many of which are different up to volume 2.03. So this is false in dimension 3.
And if you change homotopy to isometry?
It's the same. By most rigidity, counting homotopy, homeomorphism, isometry are all the same, except in dimension 2. That's most rigidity. But we'll come back to all this. But
It is true for n equals 2?
it's true for n2 equals 2. It's an exercise. It's because by Gauss-Bonnet tell you the volume tell you exactly what you see. It's how many holes, and then you can construct a triangulation. You construct a simplicial complex. So it is true in dimension 2. Dimension 1 there is no hyperbolicity, but it's true in dimension 2, and it should be true in any dimension except it's false in dimension 2. And more or less, I almost know it in all dimensions. So we will come to it. But let me just mention that in dimension 3, it is true if you restrict to arithmetic ones. So this is a recent theorem, it's not even published yet, by Nikolaj Fragik. I'm sure Raj know how to spell his name. And the proof is number theoretic, and the conjecture is true. For arithmetic 3 manifold. So it's a false statement because I said the conjecture is about non-3 manifold, but the analog conjecture for arithmetic 3 manifold is true, and the proof is nice and long, 70 pages, quite technical but beautiful, and it's a lot of number theory.
Did he prove for 3 manifolds or for all Irish?
No, he proved it for 3 manifold. He doesn't know it for 4 manifold.
Not even arithmetic.
Not arithmetic. No, he needed SL2. I think the proof is generalizable to. It should work in any case. I think, but there are hard steps there. but he did it for three manifold. I think we will discuss his proof at some point. What?
Raz to present.
So okay. So anyhow, so in dimension 3, it's still true for arithmetic. In other dimension, I want to say something because so the course ends in 5 minutes, but let me say. Let me say something about this. So here is a theorem. Something that I proved in my PhD. It's a part of a bigger theorem, but what is true is the following. There are d and alpha such that for any n which is not 3, fundamental group of M is a hyperbolic n manifold, is isomorphic to the fundamental group of R, where R is some d alpha volume M simplicial complex.
But can you put an hyperbolic metric on R?
No, R is a simplicial complex.
So
Wait. So let me say. I want to show that M is homotopic to some simplicial complex R. I cannot do that, but what I can show that the fundamental group of M is the same as the fundamental group of R for some simplicial complex who is bounded by the volume of M. And this is great for almost all applications. Why? Because we know it. Let's recall that M is Hn mod gamma. So the universal cover of M is contractible. So all its homotopic group are trivial except the first homotopic group. Except pi 1, pi 2 is trivial, pi 3 is trivial. The only one which is not trivial is pi 1. And here I tell you how to bound pi 1. If I know the volume of M, I can bound the complexity of pi 1. So it's already quite good. So, as I said, we are interested in the asymptotic of manifold. It's the same as asymptotic properties of lattices. So I don't know that the manifold itself is homotopic to a small simplicial complex, but I know that the lattice is the fundamental group of nice simplicial complex.
So you mean that like here R may have pi 2 and pi 3?
Yeah, this R will not be aspherical. This R will have pi 2 and pi 3. If it had trivial homotopy group, higher homotopy group, it will be homotopy equivalent to M. But I don't know how to do that. I can only do that it's but this is sufficiently good for many applications because I mentioned some finiteness theorem, but there are other finiteness statements, and whenever you have finiteness statement, you wish to get a quantitative statement. In the last 2 minutes, let me mention that one of the one classical result, for instance, for lattices in Lie groups is that they're all finitely generated. A lattice in a Lie group is finitely generated. So this will give you a quantitative estimate because you have a Lie group. You know that the lattice is the fundamental group of a small simplicial complex. So of course it's finitely generated. Actually, you can bound the number of generators, and you can bound the number of relations. You can bound the presentation of the lattice in terms of the combinatoric of the simplicial complex. So the volume, the co-volume controls many asymptotic invariant of the group. So in a sense, you see this theorem is quite strong already for application. And as I said, I discuss in this introductory talk only hyperbolic manifold, but you can, the same theorem applies for general symmetric spaces with some exceptions, and so it will be true for general lattices in general groups. So I will discuss that. In the last 2 minutes, I will say that next time we will start to be more rigorous, but to add to the introduction, I should say how to generalize hyperbolic to other symmetric spaces, just to mention them. And another thing is, okay, I want to explain some ideas about behind this theorem. Okay, actually, let's finish here, and next time maybe I'll say a bit more motivation before we start to be rigorous, because there are more to the story. More to, this conjecture is one cornerstone, I think, of this theory we're discussing, and I would like to aim on proving this conjecture, or what we can, and if we can prove the conjecture, we can sometimes prove the consequence of the conjecture. But another thing is more refined asymptotic properties of what's happened when the volume gets larger, things improve. So somehow we have better control on large manifold. Okay, we will discuss it, and you will get to know some symmetric spaces, some geometry of symmetric space, some rigidity theory, some theory of lattices. So these are things that we will learn on the side because we will need it. Okay, so now let's discuss a bit the time. So will it be okay